Welcome back to our coursework. In this explainer for episode 6, we're making a crucial transition. We're moving from the local minimum shift we derived back in episode 5 straight into the rigorous question of attractor stability. You see, last time we demonstrated how the baseline 240-degree minimum can shift, but today's question is fundamentally about survival. Is that shifted point actually stable? To answer that, we're going to focus our attention entirely on renormalisation-group flow, RG flow, and what it means to be a stable attractor.
You'll recall our perturbative shift formula. Mathematically, this showed us exactly how stiffness and a displaced coherent center work together to move the baseline minimum away from 240 degrees. We've seen the mechanics of that local shift. But finding a moved point on a mathematical landscape is ultimately just a local result. If a preferred phase is going to carry actual physical meaning, it has to survive a lot more than just a single local perturbation.
So today's mathematical progression is all about crossing that conceptual gap. We're going to move from a local perturbation to scale-independent stability. We'll explore why a local shift isn't enough, understand what RG flow actually means in this phase system, distinguish between a local minimum and an attractor, and then see what this all implies for the stability of our 255-degree point. Finally, we'll map out exactly what this specific lesson establishes for our broader closure story.
Let's start by looking carefully at why establishing a local shift simply isn't the end of the story.
Here's the core issue. A phase can be mathematically stationary. It can even be locally stable, but it can completely fail to hold any physical meaning if it isn't preserved under scale evolution. Think of it like this. A point might look like a perfect, stable valley when you examine it up close at one very specific scale of measurement. But in physics, we have to zoom out. We have to coarse-grain the system. If that valley just flattens out or vanishes entirely when we change our scale of observation, well then it was never a physical truth to begin with. It was just a fragile local artifact.
Therefore, to really complete our closure story, we have to move beyond perturbation theory. We need to know if the derived minimum remains stable as the effective theory is flowed from one scale to another. The question isn't just, where is the local minimum anymore? The rigorous question we have to ask is whether that minimum holds its ground dynamically across different physical scales. And to answer that, we have to introduce the mechanics of scale evolution.
This naturally brings us to the concept of evolving effective couplings, which we track using RG flow.
In the context of our phase system, RG flow conceptually involves a three-step process. First, we integrate out the short-distance, high-energy structural details. Second, as we smooth over those microscopic fluctuations, we allow the effective couplings, the parameters dictating the system's behavior, to run. And third, we carefully track how the phase landscape deforms and changes as a function of that evolving scale.
The fundamental truth here is that our effective phase landscape is highly dynamic. It is not frozen in place. Depending on the exact microscopic flow equation, the terrain actually transforms. Mountains can become valleys, and valleys can rise into mountains as you change the scale of observation. So, a candidate attractor is only physically important if it remains an enduring feature on that shifting landscape.
This requires us to draw a very strict mathematical line between true stability and mere local stationarity.
We have to contrast a local minimum with a stable attractor. A local minimum is stationary at one chosen scale, making it mathematically fragile. It really only exists in a frozen snapshot. A stable attractor, on the other hand, is mathematically enduring. It maintains its stability not just against local perturbations, but against coarse-grained scale flow. It's a state the system naturally pulls toward, even as effective couplings run.
This expression is the strict mathematical condition, ensuring that any nearby flow is pulled back toward the candidate point, rather than pushed away from it. We aren't just looking for a spot where the flow stops. We're looking for a state where any slight deviation is actively corrected by the dynamics of the system itself. The flow must converge upon the point. That's what makes it a true stable attractor. And for our ongoing closure story, the specific candidate point of interest that must satisfy this stability condition is 255 degrees. Back in episode 5, our shift derivation moved us to this exact point. Now, we're placing 255 degrees under the rigorous microscope of RG flow to see if it actually behaves as an enduring attractor.
Let's look at the central conceptual payoff here. What would true stability actually mean for our 255-degree phase?
The implications are binary and incredibly significant. If 255 degrees remains selected under RG flow, then it is a physically meaningful phase. But if it gets rejected under flow, then the shifted point was just a fragile local artifact of our perturbation. We are essentially putting the physical reality of our mathematical derivation to the test. If scale evolution washes that point away, it was just a temporary illusion at an isolated scale.
This really highlights the profound difference between a formal correction and a true attractor. A formal correction just tells you how to move a theoretical point on a piece of paper. But discovering a true dynamical attractor, that tells you that the moved minimum actually dictates the real dynamic behavior of the system across the scales of physics.
Before we wrap up, let's be absolutely clear about the boundaries of this lesson and what it frames for our next steps.
In terms of our derivation status, we have successfully established the foundational stability question. We've shown exactly why establishing attractor stability is the absolutely unavoidable next step after deriving our local shift. Now, we acknowledge that we do not yet have a fully model-independent macroscopic beta function at this stage. We aren't jumping ahead to solve everything today, but we have laid down the strict structural requirement that our candidate point must eventually pass.
To summarize our core takeaway, scale flow dictates physical reality. A locally shifted minimum is mathematically insufficient on its own because, in physics, scale matters. Achieving true attractor status requires enduring stability across all scales, not just one. Ultimately, the closure story of this framework inherently demands an understanding of RG behavior. Local stationarity alone is a piece of the puzzle, but it cannot complete the picture. We have to map how the point behaves as the effective theory scales around it. I want to leave you with this question to ponder as we conclude today's lesson. Is a preferred phase meaningful if it appears locally but does not survive flow across scales? As our mathematics have shown us today, the rigorous answer is no. True physical meaning requires endurance. A minimum may move into place, but only an attractor can endure. Next time, we ask what protects that endurance as we look ahead to Episode 7 and explore topological protection and lattice pinning.